All right, so welcome back everybody to your eighth Comp 335 tutorial. So in this tutorial, we'll be looking at, we'll be continuing our sort of study of context-free grammars. And then we're going to take a look at types of derivation orders and how they relate to ambiguity, okay? So let's start with context-free grammar. So we saw this at the end of tutorial 7, but let me sort of give you a refresher of the definition of a context-free grammar. So a context-free grammar, G, is a four-tuple of a set of variables, terminals, start variable, and production rules, where um, unlike in regular grammars, in the production rules of context-free grammars, you can have on the left-hand side a variable, and then on the right-hand side, any combination of terminals and variables. So you can not only have something like A gives you uh, a, you could also have A gives you uh, A and then maybe two variables, A, B, and then a terminal after, and then maybe another variable, and so on. The only thing that you can't see in a context-free grammar is on the left-hand side, if you get something like A, B, gives you C, then this would not be allowed. This is known as context sensitive, which we haven't studied yet. So a very natural extension of this definition is for languages. A language L is said to be context-free if and only if there is a context-free grammar G such that G generates it. So for instance, if I have a grammar G with some variables V, terminals T, start variable S, and productions P, let's say, for example, the production rules look like S gives me A, S, B, B, or lambda, okay? Then this grammar is context-free, right? This grammar is context-free, so the language generated by G is a context-free language, okay? So what's important to note here is, in fact, every regular language, so if you have a regular language, can be produced or generated by a regular grammar, and so is generated by a regular grammar G. And regular grammars are, in fact, specific or particular cases of this more general case. So regular grammars are actually a particular case of a context-free grammar. Okay, so that means that every regular language, if you think of as all the regular languages as a set, okay, every regular language is a subset of all the context-free languages. Okay, and the reason why this set here appears to be larger than the set here is because there are languages that are context-free. So there are languages in here which are not in here. So for example, the language AN, BN for n greater or equal to 0. We know that this is not regular, so we showed this with the pumping lemma. But we can find very easily the grammar, if you want the grammar S, A, S, B, or lambda. This grammar here with the variables, terminals, and start variable S. This grammar generates A and Bn, okay? So let's call this L. So L is not regular. L is not regular, but there is a context-free grammar that generates L, so L is context-free. So that means that there's a language here which is not in here. So this tells you that the set of regular languages is a proper subset. So it's a proper subset of context-free languages. Okay, so let's look at a couple of examples of context-free languages and of context-free grammars. So we have the following context-free grammar. We have two variables SA, the terminals AB, start variable S, and the following production rules here. So the first production rule S gives me ASB. This looks a lot like the one from ANBN, okay? And then instead of having a lambda here, what we have is we have a variable A that goes to another set of production rules. And here this might also look familiar. We have A on both sides of the variable A and B on both sides of the variable B. So this was like ANBN, and this was like W such that W is equal to WR. So this is a sort of production rule for palindromes. And we're going to see if the palindromes are of even or odd length. So for instance, if I need to start at S, if I want to generate a string, so I start at S, and then suppose I pick the first production rule ASB, then I get ASB, and then I replace the S with another ASB. So I get the same number of A's on the left of S as B's on the right of S. So there's 2 and 2 on each side. And if I continue this process, then I'll get n A's on the left and n A's on the right for n greater or equal to 0. And then at some point, because I want to get a string at the end of my process, I'm going to replace this S with an A, okay? So let's just look at A's for now, and then we'll combine these two sort of ideas together. So if I'm in A, then what I can do is, for instance, I could give myself an A on both sides of A, and then I could give myself B on both sides of B. So remember that the leftmost symbol here and the rightmost symbol here are the same. Same thing for the second leftmost and the second rightmost, and this sort of process repeats. Okay, so you would have the mirror image of the symbols on the left with the symbols on the right, where the leftmost matches with the rightmost. And here, because the only production rules in A that give you terminals are A gives you A or B, then in the center of your derivation of your final derived string, you would get either an A or a B. So notice here that this would mean that A produces palindromes of odd length. Okay, so now if we combine these two ideas together, then you start at S, and then you derive n A's on sort of the leftmost side of the string and n B's on the rightmost side of the string. And then once you finish your derivation in S, you go to A. So then you can think of going to A as going here, where you have a bunch of A's here and the same number of B's here. Okay. So maybe I'll write Bn and An. And then I continue that process where I get essentially a mirror image of my string on the left with my string on the right. So in fact, what I get is on the sort of left of A or B of the last terminal string, I'll get A1 through, let's say, AK. Suppose the last symbol is AK. And then on the right, I'll get the reversal of that. I'll get AK through A1. And then to pick the last terminal string, I'm going to use sort of this guy here, and I'm going to have either A or B. So then my final string is going to have the form AN on the left and BN on the right, and then a string V over AB and a string VR at the right. Okay, and then in the middle, I'll have X, where X is a symbol A or B. So in fact, this guy here if you take the reversal of this guy, what you'll get is you'll get v x reverse, but the reversal of a symbol is the symbol itself, v reverse. Okay, so in fact, this guy is, so this is a palindrome of odd length. Okay, and so we can just write that more generally as ANWBN, where W is a palindrome of odd length over AB, and that would be the language generated by G. Okay, now an exercise for you. So what language does this following grammar generate? Okay, so let's first, the first thing you need to sort of notice here is if you're at your start variable S, okay, and you choose to go to C, then you're essentially going to be stuck. So why? Because if you're in C, now what you have is, so suppose I pick, I'm in S, then I go to C, I replace S with C, and then I replace C with little c, and then variable cd, okay? And then for d, I have no choice but to replace it with little d, so suppose I do that, replace it with little d. But this c here, this variable here, is never going to become, this variable here will never be replaced by a string of terminals t, okay? And the reason why is because you're essentially sort of stuck here in a kind of an infinite loop where you never essentially terminate, and terminating in this case would mean you get terminal symbols. So what this really means is this production C gives me CCD is useless, so you can actually just ignore it. And since D is only used in this useless production, you can also eliminate this guy. And so then the production S gives me C also becomes irrelevant. So really what my sort of grammar reduces to is basically this guy, okay? So now we can sort of try to see what a possible set of strings a G would generate. So in cases like this, it's good to sort of play around with your derivations and try to see if you can observe a pattern. So, well, what's the shortest string that I can generate? If I'm an S, I can produce an A. So that would be the shortest string. Then if I'm in S, and instead of choosing the little a, I choose little a and then variable a, then I have to go to A, right? So if I'm in A, I can choose my lambda, but then I would get A, so I don't want to sort of repeat that again. So let me instead choose this production rule. So I replace A with little a b, and then from variable b, there's no terminals here, so I have no choice but to sort of go back to A by replacing it with capital A, little a. So I get A here. Okay. And then once I'm there, then I can use my sort of lambda to get A. Okay. So far we've gotten the two shortest strings of odd length with only symbols A, basically. So in other words, we've gotten the two shortest strings over the alphabet A only. Okay. So is there sort of a pattern to that? Well, to sort of notice that, you need to notice that this B here, to sort of make your life simple or simpler, you can actually replace S gives you B by something else. So if you're in S and instead you choose the production rule B, okay, then you have no choice, because this is sort of the only production rule that you have. You have no choice but to replace B by A A, okay? And then if you don't want to terminate, right? If you don't want to terminate, then what you need to do is, wait a second here. You don't want to terminate. Oh, okay, I see. Okay. So now I'm in A here. So now what is the sort of possible derivation if I'm in capital A? Well, if I'm in capital A and I don't want to use the lambda because I don't want to end yet, then I could use sort of A and then B, right? I'm using this derivation rule. And then from the B, I always sort of need to go back to A. So from the B, um, I would get A. So I replace my B with capital A. So what you need to notice here is, in fact, the B here acts as only an intermediate a state, kind of an intermediate variable. It can never give you a terminal string. The only guy that can give you a terminal string is S with the production rule A. That can only happen once. Or A with the production rule lambda. So really what you can say is you can essentially add or sort of notice that if you're an A and you don't want to terminate, then your production rule becomes A gives you little a. So essentially you have a new production rule, A gives you little a, capital A. Okay, so why is this sort of relevant? Well, it becomes relevant to sort of help you simplify the grammar a bit, sort of a bit more. So if you're in capital A, so now you can sort of replace the production rule B gives you capital A to in fact just okay. So okay, let me start that over. So after noticing that these production rules are possible, you sort of you want to find a pattern in your production rules so you can generalize what L of G is. In most cases, it's actually quite difficult to see that, but in some particular hand-picked cases, it's doable. So in this case, it's a bit tricky, but it's still doable to sort of see. So now that we've eliminated and reduced the grammar to this guy, which is still context-free, we need to sort of continue our exploration by finding the smallest possible derivations. So for instance, I have that S gives me little a. So I know that L of G is going to have a, little a at least. Then if instead of using little a, I use little a, capital A, okay, then if I'm in capital A, I can either choose the lambda, but then I would get little a. So I don't want little a again. So instead what I'm going to do is I'm going to replace my capital A with a little a capital B. So that's going to be little a, and then I'm going to replace my a with little a capital B. Okay, but what you need to notice is capital B does not have any terminals. Okay, so the only thing that it can do is it can send you back to A. So the only thing that B can do is you replace this B, capital B, capital A, little a. So you replace that with this guy. Okay. So what you need to notice essentially is the b here, your b variable here. The only thing it did is it played the role of an intermediary between this guy, so replacing this guy with this guy. So really, what you can do is you can think of as just sort of crossing out this derivation because it exists, it's still there, but you don't really care about it, and it might just confuse you more in trying to find what the language is. So then what you can do is now that you're in sort of this form, then again you can either replace with lambda, or you can replace with a capital B. But we said that replacing with a capital B is just going to lead to replacing a with little a, capital A, little a. Okay, so if I do replace with lambda, I get a cube. But what if instead, so I give S gives me little a, capital A, then I skip over the B transition and I automatically give myself little a, capital A, little a. And then I essentially repeat the process again. So I get a little a, and then I replace this capital A with a little a, capital A, little a. Okay, so what I've done now is I've given myself so I've given myself the same number of A's. So if you want this, so excluding the leftmost A, there's the same number of A's on the left as on the right. So this guy is always going to give me an even number of A's, and then this guy here is going to add +1. So an even number of A's +1 is always going to give me an odd number of A's. Okay, so that means that, for instance, S, if I replaced it here with lambda, I would get A5. And then you can see that you could also do S gives you A7, S gives you A9, and so on. So S could very easily, you can see, give you A to the 2n plus 1 for n greater or equal to 0. Okay, so for sure you have essentially you have all of the odd length strings over only A. So you have all of the strings of odd length over A. The question is, can you have more than that? So we've sort of exhausted almost all of the options, except for S gives you capital B. So what happens, maybe if you use that, if you use S gives you capital B, you can get perhaps an even number of A's. So let's continue the process here. So remember, I crossed this off and I crossed this off. So now if I use S and I replace that with B, okay, then from B, I'm going to replace that with capital A, okay. But now remember what I said is this capital A, it's either going to use the lambda. So if it used the lambda, you would get a little a. Or if it uses the B, it's just going to come back to itself. It's going to come back to itself and give you little a, capital A, little a, followed by an A. So we see that the same sort of process or phenomenon occurs, except that the extra A is now on the right rather than being on the left. So we see here that we're also going to get derivations of A where there's only an odd number of A's. And so in that case, we can safely conclude that the grammar generated by G is A to the 2n plus 1 for n greater or equal to 0. Okay, so that is the language generated by G in this case. All right, now let's switch gears. And now what we want to do is we want to find grammars that generate languages. In this first exercise, the answer is actually a bit more involved than you might think. Here we're saying give a grammar G that generates the language L, and we're asking if this language is context free. So um, you have to notice here that it's telling us to give any grammar G. So if you're allowed to give any grammar G, the easiest grammar that you could give would be a regular grammar. But you can kind of guess here that the language here is going to be non-regular. And so if you want to be very rigorous, the first thing you would need to do is you need to show L is not regular. And you need to do that via the pumping lemma, okay? So in this case, it says that we have AN, BK, CL, where L is 2K plus N. So a very easy pick for W would be if M is the pumping length, then you could pick W as AM, BM, C, 3M, because that's 2M plus M, okay? And then you would sort of continue the process of the pumping lemma. I won't do it because hopefully by now you sort of know the steps, but that would be the first step. So now that you've shown that L is not regular, there is no regular grammar G such that L of G is equal to L. So now the second thing here, the second thing you need to do is you need to try to find, so you need to check if the language is in fact context-free. So is the language context-free? In other words, does there exist a context-free grammar G such that L of G is equal to L? Okay, so that's what you're asking yourself. Can we find a context-free grammar that generates this language? Well, in fact, if you notice, if you use a very similar trick to the last exercise in tutorial 7, you're going to see that it is, in fact, context-free because there is a context-free grammar that generates. So what you need to notice is you need to notice a pattern in the strings of L. So we know that we have n A's here, and then we have k B's, and then finally we have 2k plus n C's. So I'm going to write that here as we have 2k C's, and we have after that n C's. So now what I want you to notice is we can find a context-free grammar that gives me an and then Cn. And we can also find a context-free grammar that gives me Bk and C2k. So in fact, there's nothing that should be telling you that this isn't context-free, because it very much looks like that. It very much looks like that there is a grammar G that is context-free that might generate it. So when you have examples like this, it's the good strategy to take here is you start with the outer. So you start with the outermost pattern, and then you work your way towards the innermost pattern. So in our case here, the outermost pattern is ANCN. So how do I create ANCN? Well, if I have my start variable S, so suppose G is, let's say S, I don't know how many variables yet. I have A, B, C, my start variable is S, and I have production rows P, where P is the following. So for S, I want a same number of A's as C's on both extremities. So I can just do that with A, S, C. So notice here that N, L, and K are all greater or equal to 0. So I don't have to have at least one. So then S could give me ASC a bunch of times. Or what it could do is it could go directly to this production rule here, where I get BK, CK. So let's call that new production rule A, okay? And A, to get twice as many C's on the right as B's on the left, what I do is for every B I see on the left of A, I put 2 C's on the right of A. And this guarantees that for every B, I have twice as many C's. So this guarantees BK C2K. Okay. And notice again that here K can be greater or equal to 0. So I can either have any non-zero number of B's and C's, or if I just want 0 B's and 0 C's, I can give myself a lambda. Okay, and this essentially is the grammar that generates the language L here. Okay, so another similar exercise is in this case, we don't ask you to check essentially if the language is regular or not. We automatically just say, give a context-free grammar G for the language L. So this essentially, this exercise is already assuming that L is a context-free language. Or it could also be a regular language, and we wanted a context-free grammar for it. But that's typically not useful because context-free grammars are more expensive than regular grammars. Here we want L as AMBM, where the difference between M and N is 1. So whenever you see a difference in a context-free grammar, in a context-free language description, your instinct should always be to convert to a plus, okay? And that's what we're going to do here. So A and BM such that M minus N is equal to 1 is equivalent to M is equal to 1 more than N, okay? And then at that point, it becomes quite easy because we have A. So here, suppose that M and N are both greater or equal to 0. So now, as I said, it becomes fairly straightforward. We have n a's, and then we replace m by n plus 1. We have n plus 1 b's for n greater or equal to 0. And then hopefully you can sort of almost instinctively see what the grammar could be. You essentially only need one variable s, and so you have n a's, and you have an extra, so you have n b's on the right, and then you have an extra b in the middle. So then to get the same number of a's as b's on the left and right of little b, I can do ASB. And then once I'm done doing this process, I can replace my s with a b, which guarantees that I have one more b than a's. And this becomes the grammar. If you want to be if you want to be thorough, you would say the set of variables is s, the set of terminals is ab, the start variable is s, and the productional p is this guy. And that would be your context-free grammar. Okay. Now a different one where the sort of the structure is not explicitly given to you. So we want to find a context-free grammar for the language L, where L is the same string U on both sides, and then V reverse V on both sides, and then the string W, where W has length exactly 3 and U has length exactly 2. So again, what you want to do in these types of examples is you want to work from the outermost case to the innermost case. So the first case is you want the same string on the left as on the right, and that string you know has length 2. So there's actually only 4 cases to consider. There's AA on the left and AA on the right, and then AB on the left and AB on the right, BA and BA, and BB and BB. So then all you need to do is you replace S with production rules. You replace S with the production rule AA on the left and AA on the right. and then A in the middle, where A is going to send to sort of a continuation of this process. So you're going to get this, or this, or this, or this. Okay? So that means that for now you have essentially the identical strings on the left and on the right of the string. And now what A wants is it wants essentially V reverse V on both sides of W. So if you see an A on the leftmost, side of W, then you should see an A on the rightmost side of W. So in other words, if there's an A here, then there should be an A here. And then you can sort of loop back with the variable A. Or if you see a B on the left, then you should see a B on the right of A. Okay, and once you're done with this VRV, then you need to send to W. Okay, you need to send to W, where W is any string over AB of length exactly 3. So that's what capital B is going to give you. Capital B is going to give you, so there's a couple of ways of writing this. You could list them, list all 8 of them, or you could do B gives you X, 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 where X is A or B. And then this would give you all 8 possibilities. Okay, so there would be 2 ways of doing that. And then your grammar G, you would sort of write that formally. I'll leave that for you to do. Okay, so that would be one context-free grammar for that language. And finally, the last sort of context-free grammar generation or sort of creation we'll be looking at is you're given, you want to give a context-free grammar G for the language UAWB, where the length of U is the same as the length of B. And you know that there's an A in between, basically. So how do you do this? Well, in this case, you can't sort of straight away apply outer to inner, the outermost to innermost rule. What you need to notice is this guy here is sort of one part of the string, and this guy here, the B, the singleton B here, is another part of the string. So what I mean by that, well, if you're an S, okay, then you can sort of represent this section here as A, and this section here as just, well, you could do variable B, and then B sends to little b, but let's not waste space, and let's just say A gives me on the right has a little b. Okay, and so then you're free to do what you need to do for this guy in the derivation or in the production rules of A. So if you're an A, then you know that if U gets one symbol, then W has to get the same, not the same symbol, but it has to also get a symbol. So whenever U gets a symbol, so for instance, maybe U gets an A, then W, so on the right of capital A, W should also get an A. It doesn't need to be an A though. If there's an A on the left, it could also be a B, because you don't care about what the string is. You just care about the length in this case. Okay, and then you can do the same thing if there's a B on the left, then you can get an A. So then you would get again the same number of symbols on the left and the right. Or you could do that with a B. So in fact, it's all possibilities of sort of 2 symbols, all strings over 2 symbols. All 2 length. Oh, yeah. Okay. And then the last thing you need to do is once this process is done, once your U and W's are finished, then you need to replace that with an A. So you can do that by replacing the capital A with a little a. and that finishes the context-free grammar. Again, to be rigorous, you need to say G is equal to blah, 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 and then this is the set of production rules. Okay, so that would be your context-free grammar, G. Okay, so another concept that is introduced when you look at context-free grammars is the concept of derivation order. In regular grammars, this isn't something that's required to present because the derivation order is quite straightforward. You always know what you need to replace. But in context-free grammars, sometimes what variable you need to replace, it's not always clear. So a formal definition of derivation order or a derivation sequence is said to be leftmost if in each step in every derivation, in every application of the production rules, the leftmost variable is replaced. Okay. If instead in each production rule the rightmost variable is replaced, then this derivation sequence is said to be rightmost. So you have a leftmost derivation and a rightmost derivation. So for instance, if you're given the following grammar with a set of production rules here, and you want a leftmost and a rightmost derivation for the string AAB, then for instance, what you could do for the leftmost is you start an A. Well, you have no choice but to replace it with AB, But now if you want a leftmost derivation, what you need to do is you replace the leftmost variable, which is A, with an appropriate right-hand side. So in this case, because I want AAB, I'm going to replace A with two little a's, capital A. So I'm doing capital A replaced with this guy. And then again, because I want a leftmost derivation, I'm going to replace I'm going to replace this A here with a lambda, because again, I want AAs. I'm done with the AAs, so I'm just gonna give myself a B. So now I get two little a's and then a capital B. Okay. So now essentially I can say it's a leftmost derivation, but really I'm doing it sort of just replacing what I see. So the leftmost variable here and the only variable in fact is B. So I'm going to replace it with, because I want AAB, I want an extra B. I'm going to replace it with capital B little b. So I'm replacing it with that. And then I'm replacing it with a lambda. Okay. So this is a leftmost derivation because in each step, I'm replacing it with the leftmost variable. Okay. A sort of analogous concept, but for rightmost derivation, is if you want to derive AAB with a rightmost derivation, you always replace the rightmost variable. So S gives me AB, and now I'm going to replace capital B with a production rule because I want to use the rightmost variable. So I'm going to replace it with this guy. So capital B is going to give me capital B little b. And then again, it's the rightmost, so I'm going to pick B to replace. And I'm going to replace it with a lambda. So now I'm left with AB, and now you can see that this derives to AAB. So this is a rightmost derivation because on each step, you're replacing the rightmost variable. Okay. So that's for derivation order. Let's do a sort of quick exercise. In this case here, we have a grammar G, which is a context-free grammar. So this grammar is context-free, but so G is context-free, but we can see that actually, if you sort of work this example through, the language that's generated by it can be represented by or denoted by this regular expression. So G is context-free, but L of G is, yes, it is context-free, but if you want to be even more precise, LG is regular. Okay, so yes, L of G is context-free because this grammar is context-free, but not only is it context-free, in this particular case, not in general, but in this case, L of G is regular. So it's important to notice this because in some multiple choice questions, you have the option of saying that L of G is context-free, and then you have L of G is regular. So in this case, the sort of more correct answer, even though they're both correct, is L of G is regular. This, in my opinion, this is sort of an ambiguous multiple choice question, but because every regular language is context-free, this is implied from this, okay? And this implies this, but not the other way around, okay? So it's important to notice that there are context-free grammars that generate regular languages, okay? So we wanted to give a rightmost and a leftmost derivation of 0010. So let's do it. I'm going to start with the leftmost derivation. So I always need to start with S, and I'm going to replace S with the only right-hand side A1B. But now because it's leftmost, I'm going to replace it with, I'm going to replace the leftmost variable A. Remember what I'm trying to get 00101. So I can say that this one here corresponds to this one. And so my A's, the only thing I need for my A's is to give me zeros. So that's what I'm going to do. I'm going to use zeros for my A's. So A is going to be replaced with 0A, 1B. Again, because it's a leftmost derivation, I'm going to replace A with 0, with 0A. So I'm going to get 0A, 1B. And then A is going to replace with lambda. So I'm going to get 001 B. And now I can do the sort of replacement for B. I want 01, so I'm going to replace 001 B with 0B, and then another B with 00101 B, and then I can replace that with lambda to get 00101. Okay, so this would be the leftmost derivation. And then the rightmost derivation, what would that look like? Well, the rightmost derivation would be sort of a same kind of idea. Same kind of idea, but if you start at S and you get A1B, then you need to replace it with the B's first. So you replace it with the B's first, meaning that you get 01 on the right, so you get A1, 0B, and then A1, 01B, and then you replace that with a lambda. Okay, and then you essentially repeat the same process for the A's to get 0, 0. So I'm going to write dot, 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 and that's going to give me 00101. Yeah. Okay, so this would be a rightmost derivation. I skipped some steps because I feel like it becomes more or less straightforward once you see an example. Okay, so that's for derivation order. Now, for the last concept of this tutorial, let's look at ambiguity. So again, like I said before, regular grammars, in regular grammars, we didn't need to study ambiguity because there was no ambiguity to be had. Okay, all of the regular grammars were deterministic. You always knew where you were supposed to go. But in sort of more complicated grammars, you get this notion of ambiguous grammars. So a grammar G is said to be ambiguous if for a string W in the language generated by G, there are two distinct, so completely or partially different leftmost derivations or rightmost derivations. So notice this doesn't mean that there's one leftmost and one rightmost. This is saying that there's either two leftmost or two rightmost. So this would not make it ambiguous. You would need to have either two leftmost derivations that are distinct or two rightmost derivations that are distinct. So for example, the following grammar G, where I have S gives me BS, BB, and lambda, is an ambiguous grammar. Why? Because, for instance, I know that BB is in the language generated by G, and BB actually has two leftmost derivations. So the first derivation, the first leftmost derivation is just if you have an S, replace that with BB. Okay, that's the first leftmost derivation. The second distinct leftmost derivation is instead of using this BB, I can use this BS. So S can be replaced with BS, and S can again be replaced with BS. So you're gonna S is going to be again replaced with BS. You're going to get BBS, and then you're replacing S with lambda to get BB. Okay. So we see here that there are, in fact, two distinct leftmost derivations for BB, which implies that G is ambiguous. Okay. But notice you can actually take this grammar G and convert it. You can convert it to a non-ambiguous or an unambiguous grammar simply by deleting the BB. The BB doesn't give you anything other than a faster sort of derivation for B squared. But really, if you simplified G to S gives you BS or lambda, okay, then that would be an equivalent grammar, and it would be an equivalent unambiguous or non-ambiguous grammar. Okay, so that brings us to the sort of next concept, which is of inherent ambiguity. So we say that a language, okay, not a grammar, a language is inherently ambiguous if there is no unambiguous grammar G that generates it. So in other words, a language L is inherently ambiguous if for every grammar G such that L of G gives you L, G is ambiguous. So it's impossible to find a grammar that generates L that makes it non-ambiguous. Okay. So let's look at a few examples. So the first example here that you saw in the lecture slides was the language ANBNCM and AMBNCN, where in this case there's the same number of A's and B's, and in this case there's the same number of B's and C's. You saw that this language was in fact inherently ambiguous, and that's because for any grammar G, that would generate this language, you would always get two distinct leftmost derivations for instance, A, N, B, N, C, N. So you could get A, N, B, N, C, N with the grammar that would give you this, or with, sorry, not the grammar, the derivation that gives you this, or with the derivation that gives you that. So essentially, this just says that there is no grammar G that generates this guy, which is not ambiguous. There's always going to be a string that has at least two distinct leftmost or rightmost derivations. An example of a non-inherently ambiguous language is the one that's generated by the grammar that we just saw. Okay, so in the grammar that we just saw, we had S gives you BS, BB, lambda. We said that this was ambiguous because we said that this grammar here, G, was ambiguous because the string BB could be derived twice. Oh, so this is a typo. This does not make sense. The question should be, is the language generated by G inherently ambiguous? So we saw that the grammar was ambiguous, but that doesn't tell us anything about if L of G is inherently ambiguous or not. Okay, and the reason why is we said that L of G. Well, what is L of G actually? L of G is in fact any number of B's for n greater or equal to 0. And so this grammar here, we said that we could, this language here, we said that we can find a equivalent unambiguous grammar. S gives you BS or lambda. So this is clearly unambiguous because in every derivation, you can only take one single, you have only a single choice. So there's obviously no possibility for two or more different derivations. If you only have one choice for each step, of course you can't get any ambiguity from that. Okay, so we have L of G, which is Bn, and we have another language, another grammar G. So don't confuse. Ow. Don't confuse languages and grammars. So we have another equivalent grammar G prime here, which is non-ambiguous, where L of G prime also generates L of G. So it generates the same language as the one generated by G. But G prime is not ambiguous. So this implies that L of G is not inherently ambiguous. Okay, and in fact, the reason for this, the sort of straightforward way of reasoning this would be that we know that in fact L of G is regular. So because L of G is regular, we can automatically say that it is not inherently ambiguous, because there are no regular languages L that are inherently ambiguous. And the sort of intuition behind that is because every language L has a DFA that generates it. The DFA is completely deterministic for each symbol that's going through the machine. There's exactly one transition that it can take. And so if you convert that to a right linear grammar, then the right linear grammar has the same behavior where it only has a single choice for each possible symbol in the string. It can only have one choice of production. And so the right linear grammar will be non-ambiguous. And so that's why there are no regular grammars, regular languages that are non-ambiguous, that are inherently ambiguous. What? Oh, shut up. So we have a couple more exercises here. The first one here is we want to show that the following grammar is ambiguous. So again, how do we show that a grammar is ambiguous? You need to pick a string in L of G. So you need to pick a string in L of G and show that there are two or more distinct leftmost derivations for W. So in this case, it turns out that if you do a bit of digging, AAB is going to qualify. And the reason for that is if you want to derive AAB, one way of doing that is you start at S and you replace that with AAB, and then you replace the capital B with little b, and that gives you this. Or what you could do is you replace S with AB. And to remember, this needs to be a leftmost derivation, so I replace my A with capital A little a b, and then again with capital A little a. And then because I want to only get 3 A's, I replace A with little a, B, and then I replace capital B with little b. And so this is another leftmost derivation for AAB. Okay, and finally, exercise 8. So we have the following grammar G with this production rule, and we first want to know if the grammar is ambiguous, and then we want to know if the language generated by G is inherently ambiguous. Okay, so for the first question, is this grammar ambiguous? Well, in fact, yes, it is, because, for instance, if you pick W as B, 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 A, A, then you can get 2 leftmost derivations. So what are those derivations? If I start with S, then I can replace that with BS, and then I can replace that with BBS, and then I can replace that S with, actually no, that's not right. If I'm in BS, what I need is my second production rule. So I replace BS with this guy with BS and then 3 A's, and then I replace my S with a B, so I get B cube A cube. The other way I could do it is I could start with this production rule and get B S A, and then replace that with replace the S with BS A, replace the S with BS, and then replace this S with B to get B cube A cube. So there's 2 different leftmost derivations for B cube A cube. So yes, G is ambiguous. So I'm going to continue the question here. So the second question was, is L of G inherently ambiguous? Well, to answer that, you would first need to know what L of G is. So what is L of G actually? Well, we see that we have only a few choices if you're in S. So if you're in S, then you can give yourself a bunch of B's where you have to have at least one B. So if you're in S, you could produce Bn for n at least 1. Or what you could also do is you can mix in there this production rule BSAAA. And what you need to notice here is that for every B you get on the left, you get 3 A's on the right. So S would give you, if you only use this guy, the BSAAA, if you only use this guy, you would get, if you get K B's on the left, then you would get 3 K A's on the right. And so if we sort of combine these 2 ideas together, because you can interchange the BS and the BSAAA, then together you can see that from S you can generate Bn plus K A3K, where we see that N has to be at least 1 and K has to be at least 0. So that's that. So then this would be, so then L of G would be B n plus K A3K. And so now the question we're trying to answer if L of G is inherently ambiguous. Okay. But to check if L of G is inherently ambiguous, well, first of all, to prove that something is inherently ambiguous is actually quite difficult. So in most cases, if you're asked this, it's probably no. The answer is probably no. And in this case, it's going to be no because we can produce a unambiguous grammar that produces L of G. And that grammar could be S. So this is a production rule. S gives you, so at first, what do you want? At first, you want a bunch of B's. So you want a bunch of B's, okay? And then once you're done giving yourself a bunch of B's, then you can go to the the BK A3K. So you could go to A, which gives you, for every B you see, you get 3 A's. So you have an A in the middle. But at this point, if I put a lambda here, then I would accept lambda, but lambda is not in this language because n has to be at least 1. So to respect that, I'm going to put a b, and that's going to ensure that I have at least one b in here. Okay, and you can actually verify that this grammar is unambiguous, because if you want the b's, the sort of the n b's at the beginning, the only way to do that is to start with this production rule. And then if you want the KBs and the 3 KAs after that, you need to go here and then use this production rule. You can't start with this guy and then try to go back, okay? So this sort of tells you that there's only one derivation sequence, leftmost derivation sequence, which implies that this grammar is non-ambiguous. So L of G is not inherently ambiguous. Okay. So that concludes tutorial 8. Thank you for listening, and